Good afternoon. I'm Spot On Weather Meteorologist Matthew Euler. Welcome to today's training. I'm taking a brief break from the How the Weather Works training series to go over another very useful meteorological tool. This tool is known as satellite imagery. So today I'm going to cover the different types of satellite imagery, what some of the features look like, some of the things you can actually detect on weather satellite pictures. On the cover slide today here at the opening, there's a lot that can be discerned just from this particular satellite image. Now this particular satellite image, it appears to be a water vapor image. This is a water vapor imagery. It's a special type of imagery in the middle and upper layers of the atmosphere that helps to detect all these various features. So some of them are pointed out here on the slide, but in general, whenever you have a lighter texture or a lighter color, a white color on a water vapor image, that generally indicates moisture. So if you put this whole frame, this satellite into motion, you would see the various swirls, the eddies of the atmosphere showing up. For example, in this area off the U.S. West Coast, we have vertical ascent or rising air motion associated with these clouds in conjunction with the mid-latitude cyclone. You can also identify areas where there's shortwave ridges and shortwave troughs, and then more of the circular shape here indicating some thunderstorm development over the panhandle of Texas into parts of western Oklahoma. Wherever you see the darker coloring, the darker shading, that indicates dry air is in place. And that's usually associated with the sinking air motion in the atmosphere with high pressure. That sinking air motion is known as subsidence. Additionally, you have other areas of dry air out over the southeastern Gulf in this particular image. But there's a lot we can glean from the water vapor satellite image, and we'll get into this here in a moment. So let's get into today's training. First thing I want to start off in today's training is satellite fundamentals. Now, all objects with a temperature above absolute zero or zero Kelvin are going to emit some form of radiation. And this radiation is emitted at varying wavelengths on that electromagnetic spectrum, the EMS, in the form of electromagnetic waves. Now, there's various types of weather satellite imagery out there. There's visible imagery, which relies on reflected sunlight. Visible imagery, you need that sunlight to be reflected off the clouds to really get a good image. And therefore, visible imagery is only going to be available during daylight hours when the sun's out. There's infrared or IR imagery, which is totally temperature-based. There's water vapor imagery, again, which generally details the amount of moisture in the mid-levels to the upper levels of the atmosphere. And there's also a couple of satellite types that I'm going to get into next. And these are called the GOES and POES. And just before I move on to the satellite types, just wanted to show you this brief description of the electromagnetic spectrum. Generally, on the far left, we have very short wavelengths and very high energy. The shorter the wavelength, the greater their energy is involved. And on the left-hand side of this EM spectrum, the electromagnetic spectrum, we have very short wavelength energy associated with gamma and X-rays. Then you have UV radiation, which of course that can be very harmful to us, especially in the summertime. If we're out in the sun and we get a lot of sunshine, too much sunshine for our skin can cause some very bad sunburns due to the UV radiation from the sun. Then we move into this visible light spectrum, generally between the UV range and the infrared range on the spectrum. So you have visible light that sits between those two areas. With visible light, this is very apparent when we look at rainbows, for example, in the atmosphere. And then we continue moving to the right on the EM spectrum. You'll notice these wavelengths tend to increase. So the wavelengths are getting larger and larger, and that means the energy is getting less and less, the amount of energy. And so some of the examples of longer wavelengths would be radio waves, such as radar, TV, FM, AM radio, AM radio being one of the longest wavelengths there on the spectrum. But just some interesting concepts here when we look at this EM spectrum and how we compare the different ranges. Now, we're going to talk today about the visible imagery, and we're also going to talk about the infrared imagery. But let's first talk about the two different types of satellites out there. All right, so first we're going to talk about GOES, G-O-E-S. This stands for Geostationary Operational Environmental Satellites. Right now they're known as the GOES-R series. They provide advanced imagery and atmospheric measurements of Earth's western hemisphere, real-time mapping of lightning activity, and improved monitoring of solar activity and space weather as well. Now, GOES operates at 22,236 miles above the Earth's equator, and it stays in that position in a fixed location because the speed at which the satellite is moving is equaling the rotation of Earth. And so you get the satellite to remain fixed above a certain latitude, longitude area. This allows GOES imagery to maintain that position over specific geographic regions, providing continuous coverage of an area over time to check out, see what's happening with the weather. GOES-R, known as GOES 16, was launched in 2016 and is operational as GOES East. So fairly recent additions and upgrades to the satellite program. GOES S is known as GOES 17. This was launched in 2018, is now considered GOES West. There's GOES T, which was launched in March of this year, 2022, and is now known as GOES 18. In fact, just the other day, I saw somebody sharing one of the very first images, weather satellite images, using GOES 18. GOES U is scheduled to be launched in 2024, so there's further upgrades on the way. And then GOES East and West. The two combined generally cover more than half the globe, half of the Earth, from the west coast of Africa to New Zealand, and from near the Arctic Circle all the way down to the Antarctic Circle. So GOES imagery is a very important type of weather satellite tool. Now let's talk about POES, P-O-E-S. This stands for Polar Orbiting Operational Environmental Satellites, and they provided the backbone of the global. They're the backbone, basically, of the global observing system. The current POES satellites include NOAA 15, NOAA 18, and NOAA 19. These satellites provide additional full global data coverage, supporting both the short-term weather forecasting as well as long-term climate and environmental data records. All right, so I have a lot of experience with POES, with polar orbiters. When I used to go out on ships, a lot of times for our satellite imagery, we had to wait for the polar orbiters to pass overhead. Basically, they take certain swaths of longitude as they pass overhead, and they have an ascending and a descending node. The ascending node goes from lower latitudes towards the poles, and the descending node goes the opposite direction, from the poles towards the lower latitudes, back towards the equator. But these satellites generally tend to orbit from north to south, or south to north, and they take certain swaths of the Earth, the picture of the Earth beneath them, the clouds, the weather. And so we used to always make sure we were aware when I was looking for this data on ships, always looking to see, when is the polar orbiter going to be overhead. That was very important as far as providing real-time weather support. Another thing I want to mention before I move on to the different types of satellite imagery, polar orbiters tend to have a much lower orbit closer to Earth's surface as compared to those geostationary satellites. So geostationary satellites, as I mentioned, 22,236 miles above the Earth at the equator. And the polar orbiters, I don't have the exact number on today's training, but they tend to be much closer and lower in their orbit. So polar orbiters are great as far as very high resolution details of what's going on beneath them. Geostationary are getting much better as far as resolution goes, but the polar orbiters really do provide that really good detailed look as they make as they orbit overhead over certain swaths of longitude. So I definitely wanted to mention that. In addition, of course, polar orbiters are very valuable when it comes to gathering data over the higher latitudes, the Arctic and Antarctic circles. They can. There's no distortion there. The geostationary satellites, you have distortion on the edges of the satellite. It only can see so far north or south. The GOES imagery, the geostationary. The polar orbiter is going to be able to go completely over the polar areas, Arctic and Antarctic, and get great detailed shots. So I did want to mention that as well. All right, so now let's talk about the various types of weather satellite imagery out there. And meteorologists use these tools. Sometimes you can use all the imagery together to kind of get a picture of what's going on in the atmosphere. I like to think of satellite imagery similar to a doctor looking at an X-ray or an MRI. All right, a doctor, when he gets an X-ray, is going to be looking for specific things, right? And a meteorologist does the same thing with the atmosphere, where a meteorologist is looking at the satellite pictures and trying to determine, okay, what are the main features I'm really interested in here? I'll show you a couple examples of some of the imagery that are available. Okay, so first we'll start off with infrared or IR satellite imagery. This generally tends to detect heat energy in the IR spectrum, the IR portion of the EM spectrum. The satellite image displays objects such as clouds, water, or land surfaces based on the temperature of those surfaces or those objects. IR instrument on board the satellite provides information on the temperature of land, water, and clouds. It measures the IR radiation emitted from these surfaces. And as I mentioned to start the training, we talk about satellite fundamentals. Any object above absolute zero Kelvin, is going to emit some form of radiation. It's going to be detectable by the IR instrumentation aboard the satellites, the weather satellites, which are orbiting way above the Earth. And there's different forms of radiation that are being emitted by objects. So, for example, a hotter object. Let's say we have a hotter object on the Earth's surface. On an IR image, that object's going to appear darker, and that object's going to emit much more radiation. The hotter the object, the more radiation is emitted. The colder the object, let's say snowpack, snow cover in winter, it's going to emit much less radiation. And so you can get different contrasts between water, land, clouds as well. Higher clouds are going to be colder in nature. They're going to show up brighter on IR imagery as compared to warmer, lower clouds. And we'll get to some of those examples like I mentioned here momentarily. So in general, when we look at infrared or IR satellite imagery, warm temperatures are going to appear darker on that imagery. Colder temperatures are going to appear lighter. High-level clouds, for example, they form way high up in the atmosphere, above 20,000 feet in the mid-latitudes. Those high-level clouds, such as cirrus, they're going to be brighter on IR imagery than, let's say, a lower stratus cloud. Low clouds are relatively warm and appear gray. Example of that would be fog or low stratus clouds. The thick, cold clouds appear white. So you get a tall, very tall, vertical growing cumulus cloud in the summertime, towering cumulus becoming a cumulonimbus, a thunderstorm cloud. On IR imagery, those particular clouds are going to stick out and appear much brighter and whiter color as compared to lower clouds. The chief advantage of IR satellite imagery, it's simple. It's available 24 hours a day. Visible satellite imagery, this is based on brightness of objects that scatter visible sunlight back to the satellite. So this basically involves a process of what's known as albedo. Now, albedo is simply the amount of reflection amount of energy that's reflected off specific surfaces. Okay. Cloud-free land and water on visible imagery will be dark, while snow is going to appear bright. And that has to do with the amount of reflectivity or albedo from these surfaces. For example, land and water generally tend to not reflect as much light back to the satellite sensor. They have a very low albedo, low reflectivity property, whereas snow is going to reflect a lot of light back towards the satellite sensor. In fact, snow has an albedo on the order of 90 to 95%. That's saying that 90 to 95% of the incoming solar light radiation, the sunlight hitting snow, is going to reflect back to space and back to that sensor on the weather satellite. Okay. Overall, visible satellite imagery is good in identifying the thickness of clouds. So we have to look at the thickness as well. Thicker clouds have a high reflectivity, tend to reflect a lot more light back towards space and towards the satellite, and appear brighter than thinner clouds. Visible satellite imagery can be used to distinguish between snow cover and clouds, given that surface features such as lakes and rivers can be observed. I'm going to show you an example of a snow-covered ground here on satellite imagery shortly. But in general, if you were to try to determine the difference between snow, cover, and clouds on a winter day, what would be very useful would be to put the satellite into animation mode to loop the satellite, and of course the snow cover is going to stay stationary, whereas the clouds are going to move. But we'll get to that here in a moment. Visible satellite imagery cannot detect clouds at night. Remember that visible imagery is relying on the brightness of objects that scatter visible sunlight back to the satellite, the albedo. And you got to have the sun out to have that light reflected. Once we get to night, we don't have that. So now we have to revert to IR, infrared imagery at night. Here is a look. I saved this little chart down here at the bottom right, just showing you the albedo of reflectivity of different surfaces. By the way, on the y-axis here, the albedo ranges from 0 up to 1. And on the x-axis, the horizontal axis, it shows the wavelength in micrometers here. This is the wavelength, okay? So in general, I just want you to pay attention to the fact that snow has a much higher albedo. See where it's at on the chart? It's much higher up, 90% or greater albedo for snow. And then you go down to deciduous forest, grass is about 50% albedo, dry sand tends to drop off, and you know this from being on a beach on a hot summer day. During the day, there's a lot of absorption of heat. There's not much reflection of heat off sand, or reflection of sunlight off sand. There's a lot of absorption of light, and that turns into heat. And so when you're walking across a beach, you know how hot it is if you're walking barefoot on that beach during the day. And that has to do with the sand, the property of sand. It has a lower albedo, lower reflectivity, which results in a hotter surface. Dry grass is also very low in albedo or reflectivity. So I just wanted to show you the comparisons of these various surfaces and how much reflectivity they're going to send back out to space and eventually to the satellite image. Next type of satellite imagery we're going to talk about is water vapor satellite imagery. This is going to indicate how much moisture is present in the upper atmosphere between 15,000 and 30,000 feet. What's really a good useful tool for water vapor satellite imagery is you can get a really good, you put this thing into motion, you loop the satellite images on a water vapor imagery, and you can get a really good look at what's going on in the atmosphere, the flow patterns. Higher moisture areas on a water vapor image are going to be whiter in color, while lower moisture areas will be darker in color. And this is very useful satellite image to use for indicating where heavy rain may be possible, to identify the jet stream location. The jet stream location is usually going to be an elongated, dark area on the water vapor satellite image. So if I'm looking at this image in the bottom right here, this dark area that extends from southeastern Utah up through western Colorado, northwestern Nebraska, into South Dakota and Minnesota, this is some sort of jet stream right here. See how elongated it is or stretched out that dark area is? Meanwhile, over southern Illinois and southeastern Missouri, there's a lot of moisture present in the atmosphere. So this may be a summer day, and this might be associated with thunderstorms over southern Illinois and southeastern Missouri. So you notice the contrast in the colors on a water vapor image. All right, so now let's go into identifying some of these features on satellite imagery Now we're looking at identifying specific clouds, and we're going to start with marine stratocumulus clouds. All right. Now this type of detailed imagery is going to be available on visible satellites types, the visible imagery. All right. So generally, what can we tell from this picture I'm showing you? Okay. First of all, marine stratocumulus clouds. Stratocumulus, strato meaning layer, cumulus meaning puffy, but generally they're layered puffy clouds. They don't grow very tall in height in the vertical, and they generally are on the eastern, more stable side of high pressure over the oceans. So marine stratocumulus clouds, you're going to see these type of clouds generally in the eastern ocean basins on the stable front side of anticyclones, okay, with clockwise flow around these anticyclones. So typically marine stratocumulus clouds are located at low altitudes over the water below 6,000 feet. And by the way, this type of cloud covers about 20% of the low latitude oceans, believe it or not. They usually form over water and have either closed or open cell forms. Now I wanted to show you the differences between closed cell and open cell on this particular image. And by the way, these images are provided by Noah Nesdiz. So you notice the closed cell stratocu, how much closer they are spaced together. There's not really many openings between the individual cloud elements, whereas the open cell are on the left-hand portion of this image. And notice with open cell how they have these openings, these dark areas, these spaces where air sinks in between the individual cloud elements. So open cell cumulus versus closed cell cumulus. And closed cell, by the way, cover nearly 100% of the underlying Earth's surface and reflect a large portion of solar radiation. Now this makes sense, right? With closed cell, with the cloud elements being so closely spaced, where there's hardly any breaks in the cloud for the solar radiation to make it through to the Earth's surface, this makes a lot of sense, actually. Complete sense in that we have closed cell stratocu. They're going to reflect a lot of incoming solar radiation back to space. Not much is going to get through this cloud deck. Open cell, on the other hand, they have these broken cloud structures that surround areas of clear skies. Where you see the darker areas here on the left portion of the image, that's where the air is sinking. Where you see the cloud itself, the air is rising. Again, marine stratocumulus clouds that tend to form in eastern ocean basins on the stable eastern side of anticyclones. Wave clouds. Now these are interesting clouds. Okay, the map I'm showing you on the left here, this is Virginia and this is West Virginia. Okay, and so notice this ripple type of shape, ripple waveform type of shape. Okay, they typically occur downrange of a mountainous area with a perpendicular wind component. So these ripple cloud patterns, these are called wave clouds right here. They form when stable air moves up and over raised land features such as hills or mountains, and the air is forced upward over the top of these hills or mountains. In this case, we have the Appalachian Mountains, generally in this location, and the wind is blowing from the northwest on this particular day, and I generally have downstream of the mountains, I have these equally spaced wave clouds. All right, so clouds form on the cool crest of these waves when enough moisture is present. And I'm going to show you what this looks like here in a minute. As the air moves downward, it encounters increasing atmospheric pressure. As air sinks, it adiabatically warms, compresses, dries out, and wherever you see like these openings between the white cloud elements here, that's where the air is sinking. As air rises, it cools and condenses, forming the clouds. You see the white lines here on the satellite image, on this visible imagery. Let me draw out what's happening here, okay, to form these wave clouds. And sometimes they take the shape of almonds. They've been mistaken for UFOs by people because they have, almost like a saucer shape. But what's happening here? Let me just draw out a mountain here. Let's imagine this is a mountain range, okay? And generally I have the wind blowing up against the mountain range here. from a perpendicular component, okay, to the mountain range. All right. As the air goes up and over the mountain, what happens is you get like this eddy effect downrange of the mountain like this. Okay, so you have some ups. And this is downrange, a very strong wind blowing perpendicular to the mountain range. So you have a motion where the air goes up, then it comes back down and sinks over a short distance, then it goes up again, and then it sinks again over a short distance, then it rises or goes up again in the air. And so you get this wave-like structure like this. Very wavy motion, up and down motion. This is a very dangerous area as far as turbulence goes for anybody flying. You definitely don't want to be flying any area associated with these wave clouds in here where that motion is quite turbulent. Rising air, falling air, rising air, falling air over short distances. But it forms these gravity waves. And generally what you get are these almond-shaped clouds. They're called altocumulus lenticularis that can form downrange of the mountain itself. And I've seen these clouds in Virginia, in fact. Let me go ahead and erase this. I've seen these clouds in Virginia plenty of times, actually, and it's really amazing how far downrange that you can see these clouds. And it really is dependent on the strength of the wind. The perpendicular component is there, but how strong are these winds blowing? How strong is this wind blowing from the northwest? It probably was pretty strong on this particular day because you see how far downrange these lenticular clouds or these wave clouds get. Now let's move on to a discussion on a feature known as cloud streets. What happens, now we're looking at the east coast in this visible satellite image here. What happens, especially in wintertime, is you get cold, dry, continental polar air that tends to blow from the northwest. The winds blowing from the northwest, pushing this cold continental polar air into the east coast, the eastern seaboard. And as this cold, dry wind blows from the northwest out over the relatively warmer waters of the western Atlantic, specifically the Gulf Stream, that warm ocean current, you can get clouds to form. These cloud streets form. And the cloud streets are orientated parallel to the surface wind. So by me just looking at the orientation of these cloud streets, I know this particular day that the wind is blowing from the northwest, parallel to the individual cloud streets. Now, cloud streets are just wispy parallel lines of clouds that form off the east coast of continents. They're known as cloud streets. And cloud streets can also be prevalent off of Asia, over the western Pacific as well, when extremely cold air, whether that be continental polar or continental Arctic air, tend to move off the landmass over the relatively warmer waters of either the western Atlantic or the western Pacific Ocean. These parallel bands of cumulus clouds are often visible in satellite imagery during the colder months of the year. This is when they're most prevalent, especially late fall and early winter. They're caused by colder air advection moving off the coast. And as that colder air moves offshore behind a cold front, the heat and moisture from the relatively warmer water surfaces tends to get picked up from the relatively warm waters. Note the gap also. I want you to note the gap here between the clear area just offshore, just off the east coast, and when these cloud streets start. The sky is clear near the coast. This usually happens because the cold air has not traveled far enough yet over the water to pick up the heat and moisture. So the cold, dry air produces clear skies along the immediate coastline, but then as soon as that cold, dry air moves over the relatively warmer waters, picks up moisture from below and forms these cloud streets. So that's another neat tool about looking at satellite imagery. You can tell the wind direction. You can tell what's going on in the atmosphere. But, is it a cold day or a warm day on the East Coast? I could tell you by looking at this in wintertime, if I saw this with all these cloud streets, I would definitely be thinking it was a cold day. Moving on now to another interesting feature that shows up on weather satellite imagery. This is smoke. Of course, the western U.S. in particular has a lot of wildfires, especially as we head into the September-October timeframe in California with Santa Ana season in effect. In this example, we're showing the Kincaid Fire of California. This is north of San Francisco. you see this wispy appearance of smoke. And you can tell the direction of the winds, too, by looking at this image. And if I were to put it in motion, I'd be able to tell, okay, the wind must be blowing offshore from the northeast on this particular day because my smoke plume is going to the south. It's basically working its way from right to left in this picture. So, again, being able to detect features such as these smoke plumes from these fires and watching the drift of the smoke can help determine what type of wind I have, the wind direction for that particular day for an area. Another neat thing we can do with satellite imagery is we can tell the time of year, the seasons. Really phenomenal. Now, in both of these images on the left, the far left image is the Earth at the summer solstice around June 21st, and the image here on the right is the winter solstice, December 20th, that time frame. Note there's a dark line here. See this dark line, the dark area of Earth? That area of Earth is experiencing nighttime. Or they're just not experiencing sunlight at all in this case. So there's varying degrees of sunlight in these two images. And note during the summer solstice on the left, okay? By the way, this is north up here. This is the north. This is south down at the bottom of each image. So notice over the northern areas of the world how those areas are in light. They're getting sunlight. Notice in the southern hemisphere, here at the bottom part of this image on the left, how it's completely in darkness. So this would be an example of the summer solstice where there's 24 hours of darkness at the South Pole, and then there's 24 hours of daylight up at the North Pole. And so just by looking at a satellite imagery to determine where that line is, what areas are in the sunlight and what areas are in darkness, that really gives me a clue as to what type of time of year it is, what season we're in. Now look at the image on the right. Now we're just flipping things. At the winter solstice in late December, now the South Pole is pointed towards the sun. North Pole is pointed away from the sun, and now we have the South Pole in 24 hours of daylight in late December, and then that North Pole is in complete darkness. So just wanted to show you, this is really cool. You can even use satellite imagery to determine the seasons. Another interesting feature on satellite imagery is what's known as the Terminator. Okay, I'm trying to do my best Arnold Schwarzenegger impersonation here. The Terminator. The Terminator is the line that divides daylit areas from dark areas on Earth. It's basically your day-night line on a weather satellite. If we look at a global satellite image, you would see this vertically oriented line, and it's going to go from the east towards the west. Okay, so east towards west. And it moves on a daily basis around the Earth. Of course, every day is 24 hours. And the sunrise-sunset times are going to change throughout the course of the year depending on your latitude, where you're located on the Earth, and the time of year, the season. But in general, this is the Terminator line. So anywhere in the dark to the right portion of this image, it's night. And anywhere to the left on this satellite image, it's daytime. Another interesting feature on satellite imagery that we can determine and see is what's known as sunglint. Now, sunglint occurs as sunlight is reflected off the water at the same angle that that satellite sensor is viewing it. A bright area of light over bodies of water that gleams or sparkles. So in this particular example on the left, you notice this brighter coloring here over the ocean. This would be your sunglint. This generally will move from east to west. If I were to put this in motion, the sunglint is going to move from east to west, and it generally indicates the location where the sun is directly overhead. And also sunglint, in order to get this, you need to have a smoother ocean surface. Okay? You have to have a smoother ocean surface, smoother ocean water. If this water is choppy, there's a lot of wind energy, and the wind waves are higher, so you get your increased sea state, you're not going to be able to pick the sunglint up as readily. So just by looking at the satellite image, the brighter area here is sunglint. I know that, so I know my sun is directly overhead this particular latitude and longitude. I also know that this area has smoother seas when I see this. The seas are not rough, so that also tells me the winds are most likely light as well. When my sea state, my seas are pretty calm, that means my winds are light too. So that would be a favorable area if I were on a ship to go into. One of the coolest features with weather satellite imagery that really sticks out to us are thunderstorms. This is an example of a visible image of what thunderstorms look like. In these towering cumulus clouds as well. We have cumulus clouds, they're very speckled in nature like this. So these are more the cumulus clouds in the image. Where I have the red arrow pointed to, those are your thunderstorms. Okay. So as you can see, these thicker clouds, they definitely are apparent on this particular image in thunderstorms. Now in IR imagery, thunderstorm cloud tops are bright white due to very cold temperatures as that cloud rises in the vertical into the upper atmosphere. Okay, now let's turn our attention to the winter season type of satellite imagery. This on the left is a visible satellite of snow cover. Notice the stripe of snow, and it goes pretty far into the south. This is Alabama down here. This snow cover stretches across northwestern Georgia, eastern Tennessee, western North Carolina, on into parts of Virginia. All right, and so you notice the nature of the snowpack. And usually the rivers and the lakes within this band are going to be snow-free, and so you can readily tell snowpack because you'll see these dark lines. Like this is an example of a river right here. I can see on the image. That might be, I don't know if that's a Tennessee river or not, but it's one of the rivers in Tennessee. So if I put this whole satellite picture into motion, I would be able to see that snow cover is stationary while the clouds move as well. Now look at what's going on here. We have cloud streaks in this image as well in the lower right-hand portion. We just talked about these. Notice how clear it is along the immediate coastline of the Mid-Atlantic, southeast coast. And notice it remains fairly clear until you get a certain distance offshore. That's telling me that these winds are from the northwest on this day. So this was a colder day across the Mid-Atlantic down the southeast coast when we have these cloud streaks just offshore. Additionally, when we look at mountainous areas and we use visible imagery, we can pick up this dendritic pattern with mountains, snow-covered mountains. And so you notice how these patterns are very dendritic in nature. If I saw this on a weather satellite imagery, I would know that those are that's mountainous terrain, and this is snow-covered mountains. So just wanted to show that as well. Now let's take a look at our not so hip weather element on satellite imagery. That's fog and low stratus clouds. These are those dull gray clouds where the day seems very dull and gray the whole time. Don't get a lot of popular press in meteorology because they're not a cloud that produces lightning and thunder or anything exciting. But showing you an image here on the left, a satellite image, generally of a area of stratus, or perhaps this might be fog on a particular day. Notice the rather gray featureless cloud sheet on the satellite image, and they tend to be in certain pockets. In this case, we have the Chesapeake Bay. To me, I'm guessing that the winds are from the east on this day. Actually, the wind barbs prove that. The winds are coming in off the cooler waters of the Atlantic Ocean and producing this low stratus over Virginia, eastern portions of Virginia. Now look at river fog on an IR satellite image here in the bottom right. Now this is cool. These lines here that are encircled, this is the actual rivers. And you have a low gray stratus cloud over these rivers. And you can see how it's just over the rivers. So this is an example of river fog and what it would look like on satellite imagery. It's really cool. You can trace out where the rivers go just based on where the stratus clouds are located. So really neat stuff. And here's some other various cloud types I like to show you. On this particular image on the left, see these wispy clouds here? Those are those high ice crystal clouds, well above 20,000 feet in the atmosphere. the wispy nature gives it away that these are cirrus clouds. There's some more cirrus clouds at this location here. Look at how much brighter and more circular. I look for the circular shape on a visible satellite imagery here for identifying thunderstorms in this case. So notice the circular nature to this cloud field, and the very lumpy texture to the cloud field as well. These are cumulonimbus clouds. This is where I have an area of thunderstorms that's developed. And you can see another smaller concentric area to the northeast of this one. And so these are where your thunderstorms are developing. The little speckly clouds here in the satellite image are your cumulus clouds, those puffy clouds you see on a hot summer day. That's what they look like on a satellite image. And then over here on the upper right, this is an IR, infrared, measuring temperature. Generally, you have cirrus clouds here, very wispy look to them. Now, what can happen sometimes with thunderstorms is we get a case where the updrafts, the upward directed air is so strong that it can actually punch through the stable stratosphere, the lower parts of that stratosphere, that second layer in the atmosphere, and produce a condition known as overshooting tops. Now, you get overshooting tops of some of the strongest thunderstorms on Earth. We may have thunderstorms extending all the way up to 70,000 feet above the ground in this case. We may have a special type of thunderstorm known as a supercell in this case as well, where we get very intense, very strong updrafts, unstable air punching through the lower layers of the stratosphere, and they create these little bumpy textures. You see these little enhanced areas? These are the overshooting tops and what they look like on satellite imagery. Showing the circular shape of a thunderstorm complex over northeast Texas on the particular image here in the middle. And then I'm showing some additional overshooting top imagery. This is going into southwestern Oklahoma on this particular day. And so from thunderstorms and overshooting tops, when I see overshooting tops, I know these storms mean business. I know they're very, most likely severe, producing the possibility of producing large hail, potentially tornadoes. When I just look at this image, that's what that tells me. So looking for a bumpy texture on visible satellite imagery, a bright appearance on IR imagery due to the colder cloud temperatures at the tops of the clouds, distinct shapes. Thunderstorms could take on a circular shape like this, or they could become elongated more like this image in the far bottom right. See how it's stretched out, more elongated? Sometimes you get what's known as a V-notch, and I don't really have an example of that here to show you, but generally you have two airstreams that kind of major diffluence of airstreams. Let me show you what that looks like real quick. When you get a V-notch, it's basically like this. So if it's like you have one airstream going that way, another airstream going that way, these airstreams are diverging or spreading apart, and you usually have an intense thunderstorm complex in here. Okay, and I've seen these V-notches especially prevalent in the Gulf of Mexico before. But whenever I see a V-notch shape, and you kind of see the V-notch shape here, that generally indicates a very intense group of thunderstorms. Okay, go ahead and erase this, and we'll move on. Okay, oops. Okay, so moving on. Mid-latitude. There's a lot of interesting shapes that take place on weather satellite imagery, which tell me a lot. They could tell you a lot too at home where you're watching this from if you pay attention to it. Now, intense mid-latitude cyclones, very, very common shape. You're going to get a comma head shape here. Okay, you notice this very curly Q shape to mid-latitude cyclones. Okay, very common. In this particular satellite image right here, I can glean a lot of information. Let me show you. This is a very intense mid-latitude cyclone. It's moving across the United States, most likely from west to east. But I can show you that you probably have an area of low pressure over southeastern Colorado, and you most likely, forgive the coloring here, I know it's not matching up with what you'd use on a surface map, but you have a cold front that extends like that, okay, based on the cloud shapes. And then, maybe this is occluded. This is most likely occluded at this point. Okay. Then you have a warm front that extends out like this. All right. This is a warm front with your semicircles on it. Okay. And I can tell all of this. You probably have intense precipitation occurring in these brighter cloud areas on this IR image to the northwest of the surface low. That's your deformation zone. And you probably have some strong thunderstorms, perhaps a squall line across parts of eastern Oklahoma and East Texas on this day. You most likely have very strong southerly flow ahead of this cold front as it moves in from the west. And so you probably have cooler air up here to the north. Okay, this is the cool sector of the storm here. Of course, you have colder air back behind the cold front on this particular satellite image. And then you get a heavier strip of precip where I basically made this shape here to the northwest of the surface low. And most likely you're getting severe thunderstorms out here in the warm sector of the mid-latitude cyclone. Okay? And I can tell all of that by just looking at this satellite image. So like I said, just like a doctor analyzing an x-ray, looking for specific features of a bone, I'm looking at the weather satellite to determine what's going on in the atmosphere. I'm taking an x-ray of the atmosphere, and it's giving me all of this information here that I just spelled out for you. I didn't mention, but there's most likely probably an area of overrunning precipitation, more continuous precipitation in stratus clouds right at this point. Okay? So there's a lot of great information you can glean from satellite imagery. But this is the comma-shaped cloud structure of a mature mid-latitude cyclone for sure. And you have these conveyor belts. I'm showing them down here in the bottom right. There's various conveyor belts which transport either cold or warm temperatures, various moisture properties in conjunction with the mid-latitude cyclone. You can get a feature known as a baroclinic leaf here in the bottom left. And that baroclinic leaf has more of an S-shaped pattern like that. See that? Okay. So I know with a baroclinic leaf, this is usually going to separate two contrasting air masses. Additionally, with a baroclinic leaf, that's the first sign of an area of low pressure or storm system developing in the mid-latitudes. So that shape tells me a lot of what's going on, what I can expect at least very soon. And then I wanted to end today's training by showing you today's visible satellite picture and what may be going on in this image. Okay? First thing that might catch your eye on today's visible satellite picture would be this major area of cloudiness. It's bright in nature, isn't it? It's bright white in nature. It really stands out compared to the rest of the satellite image over the eastern U.S. Look at this thing. This is over the western Atlantic. It stands out. In fact, I see a little bit of banding here, right, with these clouds. You notice these clouds down here? The way they're structured like this. This is an association with our first tropical storm of the Atlantic season in 2022. And this tropical storm has been classified as Alex. Let me see if I can actually, forgive my writing, see if I can actually spell it out. So this is Alex right here. This is Alex. Tropical storm Alex over the western Atlantic. Of course, it's moving this direction and away from the east coast. So we're not expecting much in the way of impacts along the coast. Maybe a little bit of increased rip current and swell in this area here. But other than that, it's heading out. But look how nice the weather is. This is visible satellite imagery, right? I want you to pay attention now to the areas of clear skies. See, there's no clouds in this area specifically today. Okay? So it's a gorgeous day. So when I see this clear area, absolutely no clouds on a visible satellite imagery, you know what I'm thinking? I'm thinking that there's subsidence at this location or sinking air motion. High pressure is dominating this area of the coast today. And then moving further back, I've got some speckly clouds here showing up. These are my cumulus clouds. On the back side of this high pressure system, I have some, I'm going to abbreviate it CU for cumulus, so Q clouds. I have more cumulus clouds developing here along the coast of South Carolina, down to southern Georgia, South Alabama, southern Mississippi, Mobile, Pensacola area. You notice these areas here, they're a little bit brighter, aren't they? You notice these areas here, these splotches? Those look like they're developing thunderstorms because they're definitely not your typical cumulus clouds, which you see these little speckled nature clouds. There also looks to be some kind of enhancement of clouds here along the coast, just north of Jacksonville. A little brighter feature there, and that looks to be like a thunderstorm developing as well. And then there's another bright area here over southern Illinois that might be associated with some type of precipitation. Let's see. Have some clouds up to the north over eastern Pennsylvania, into northern Ohio and southern Michigan there. So there's a lot of interesting things we can glean just by looking at a weather satellite imagery. Look at all the information that we determined today by just looking at this. Okay, so again, it's a great tool for meteorologists to use. Beginning with Tyros, the launch in 1957, the beginning of the weather satellite era began. And I mean, can you imagine before satellites were around, especially when we talk about the tropical areas of the Earth, the hurricane season, how you would not even be able to detect the hurricanes in advance to warn people if there was no weather satellites yet to view these storms. So just satellites have come a long way from their infancy back in the late 1950s to present day. I probably should have saved it. It would have been cool to show you. But GOES 18, I just saw one of the first images from it the other day. It's just amazing what you can glean, the amount of data and information you can glean from these weather satellites. All right, that wraps the training up today, everybody. I certainly hope you enjoyed today's training on satellite imagery. We talked about a lot of different things, a lot of basic fundamentals about satellites in general. We talked about looking at the different types of satellites, the GOES, the geostationary satellites, as well as the POES, the polar orbiting satellites. We talked about the various three types of imagery that we look at: infrared imagery, IR satellite imagery. That's detecting heat energy in that IR portion of the EM spectrum. Whether different objects are going to emit different forms of radiation depending on their temperature overall. Okay. We talked about visible satellite imagery based on albedo and reflectivity. And we also talked about this chart here at the bottom, bottom right, which showed the various forms of reflectivity or albedo from the surfaces: grass versus snow versus deciduous forest versus that hot sand in the summer on those beaches when you feel like the bottom of your feet are going to burn up. We looked at water vapor satellite imagery, the importance of this to give us those mid and upper level flow patterns. How are my systems moving? Where are my eddies at, my lows, and my high pressure systems, my swirls? We can identify the jet stream location using water vapor satellite imagery. Then we talked about some of the detailed features we can glean from satellite imagery, including these marine stratocumulus clouds, whether they be closed cell or open cell. Wave clouds, one of the coolest clouds you'll see downrange of mountains. Talked about cloud streets and what they generally indicate. And then smoke plumes, and we can tell the upper level winds and which way that plume is moving gives us that indication of the upper level wind direction. We talked about using satellites to determine what time of year it is, between the difference between summer on the left-hand portion of the image and winter on the right-hand portion. We talked about the Terminator line, Sunglint, thunderstorms, and other features, what snow looks like, what fog and stratus look like. They're much duller gray in appearance, rather featureless on IR imagery compared to snow. Okay. We looked at various types of clouds, and then thunderstorms and overshooting tops, mid-latitude shapes, and what I can glean, the amount of information I can glean from that. And then we looked at today's satellite image and just said, let's identify some features using what we just learned earlier in the training to figure out what's happening on today's weather image. So satellite images can do us, it's just amazing what kind of tool this provides. And that's it, everybody. I'm wrapping things up. I hope everybody's having a great day today. I'll continue on with my meteorology history series upcoming. I've got a video ready to go on Carl Gustav Rossby. So I'm going to continue moving forward with meteorological pioneers and detailing their fine work. And then I'm going to get right back into How the Weather Works training series soon. And the next training topic is going to be thunderstorms. So lots of training ahead. Lots of fun here on the Spot on Weather YouTube channel. Thank you so much for watching, taking time out of your busy lives. I wish everybody great health and happiness. And until next time, everybody, take care and God bless.